Okay. So today we are going to start October-November 2022 paper 5-2. Let's start with the question number 1. Eggshells contain a high percentage by mass of calcium carbonate. Please give me a minute. Yes. So eggshells contain a high percentage of a mass of calcium carbonate, CaCO3. A student wants to find out percentage of an eggshell. What percentage of an eggshell is calcium carbonate, and uses the following method. Okay. So here there is a method. The method uses a known excess of acid to dissolve the eggshell. Yes, because it have a calcium carbonate, so it would react with the calcium carbonate, forming a salt water and carbon dioxide. The amount of unreacted acid is then determined by titration with an alkali. So it means we are using excess of acid, and the rest of the acid, after the reaction is completed, we will do the titration with an alkali to find out how much acid is left behind, so we can able to know that how much acid is being used with the eggshell. Assume the acid only reacts with calcium carbonate in the eggshell. Okay. Now let's discuss the step. Step number 1: wash an empty eggshell with distilled water. Okay. Step number 2: warm the eggshell in an oven for a few minutes until dry. Okay. Then in step 3, grind the eggshell into powder to increase the surface area. And then in step 2, it was dried in oven for to make sure that the water must evaporate. Step number 4, weigh approximately 2 grams of eggshell powder into a conical flask using a balance which measures to 3 decimal place. So see, they have given you the information that the balance is of 3 decimal places. So it might be that they are going to ask you about the error. Let's see. Now in step number 5, okay, add 100 centimeter cube of 2 mole per dm cube hydrochloric acid to a conical flask. Okay, so we have a concentration of acid and a volume of acid. Loosely cover the conical flask and leave for 2 days. Okay. Filter the contents of the conical flask with any risings into 250 centimeter cube volumetric flask and top up to the mark using distilled water. Okay. So we have diluted it further and make the volume to 250 centimeter cube. Transfer 25 centimeter cube. Okay. Of the solution prepared in step 7 into a conical flask and add of thymol blue indicator and titrate against 1 mole per dm cube sodium hydroxide. So here we have a concentration of a base or an alkali using 50 centimeter cube unit. Okay. First, tell me if the method is clear to everyone. Yes, Soleha, Ahmed, Mariam, and Alisa.
Yes, sir.
Yes.
Okay. Now let's proceed. The calcium carbonate in eggshell reacts with the excess hydrochloric acid as follows. Okay, here we have a chemical equation. The excess acid reacts with the sodium hydroxide solution as follows. So this one is going to be a reaction 1 when we put up powdered eggshell in an acid, then this reaction would occur, the reaction number 1, and the reaction number 2 is the titration when the all the eggshell is reacted. Afterwards, we titrate the solution to identify or determine the amount of acid that is left behind. So for that, we will do the reaction number 2. Suggest, okay, suggest how the student could confirm the eggshell is completely dry in step 2. Yes, I think we have discussed same sort of question. So any one of you who want to suggest the answer? Have a look at step 2. Now, see, they have,
Keep warming until mass is constant.
yeah, very good. So they haven't mentioned that we are reheating. They have just said that for few minutes. So it means reheat and reweigh until mass is constant, right? So if the mass is constant in the two readings, it indicates that all the water must be lost. Okay, now state why the eggshell is made into a powder in step 3 before making up the solution. Explain your answer. So we know that uh, breaking the larger lump or a bigger piece into a smaller ones increases the surface area. And if the surface area is increased, then the rate of reaction is increased, right? So I can write over here that powder eggshell have increased surface area and hence the rate of reaction increases. Is this understandable, this part? Yes.
Yes, sir.
Okay. Now, suggest why the solution is left for the 2 days in step 6 before being used. Yes. So if you see step 6, what we did after adding the hydrochloric acid to the conical flask, we left it for 2 days, and it is why, because to make sure that the reaction must be completed. So it is to make sure that the reaction is complete. Is this clear to everyone? Now, B part, the student uses exactly 2.136 gram powdered eggshell and obtains the results shown in table 1.1. So the examiner says that we are using 2 grams initially in the method, approximately 2 grams, right, in the step 4. So the exact or the accurate or the precise mass that is used is 2.136 grams. Now here we have a table 1.1 which shows the titration results. Okay. Now we have to find the titer. So for the rough, it is 16.55. For the first one, it is 16.30. For the second one, it is 16.10. And for the third one, it is 16.20. Okay. Calculate the mean titer. So if you recall, the mean titer would be one with the two readings. If there is a two concordant readings with a difference of 0.1 centimeter cube, right? But here, if you see these two having a, you know, no, 1 minute. I've subtracted from, so it is 16.00. So these two having a difference of 0.1. So to find the mean titer or the average titer, we give take the average of these two values only. So 16.20 plus 16.30 divided by 2. Let me tell you, if the case is that instead this we have a 16.10, then can anybody tell me how could we take the mean titer in this case? Yes, Solena, good. We will use all three values. Okay. So in this case, because these two, in this case, these two have a difference of 0.1 and these two have a difference of 0.1, right? So that's why we take all the three values to take the to find the mean titer or the average volume of the titration, average volume of the titration. Now, here, what you are going to get? You are going to get 16.25, and the mean titer would be 16.25. Okay. Is this clear to everyone? Now, next part. Calculate the amount in mole of unreacted hydrochloric acid in the solution prepared in step 7. Show your working. Okay. So, in the burette, we have a volume that is used of sodium hydroxide, right? And what is the concentration of sodium hydroxide that we have used? Here we have the concentration of sodium hydroxide, 1 mole per dm cube sodium hydroxide. Okay. So first, what we would do, we would find the moles of sodium hydroxide. And let me tell you, if you recall, the moles of hydrochloric acid would be the same as well, because see over here, their mole ratio is 1:1, right? If their mole ratio is 1:1, then the moles of hydrochloric acid would be same as the moles of sodium hydroxide. So the moles of sodium hydroxide would be determined by multiplying the volume times concentration, and this volume must be in centimeter, this decimeter cube, so I have to divide it by 1000. So can anybody tell me the value, please? What value we are getting over here?
Zero point 0.01625.
0.01625. These are the moles of HCl that are reacted with okay, 1 minute. Reacted with sodium hydroxide. Now, if you read the question again, they are saying that calculate the amounts of in moles of unreacted hydrochloric acid in the solution prepared in step 7. So these are the moles. And if you see the volume that is used for the titration is 25 centimeter cube. And this 25 centimeter cube is taken by 250 centimeter cube, right? So if these are the moles of hydrochloric acid that is reacted with sodium hydroxide, it means these are the number of moles of hydrochloric acid that are actually, left after the reaction in 25 centimeter cube. But the volume that we have prepared the solution is 250 centimeter cube. So we would find the volume, the number of moles in 250 centimeter cube. So 25 centimeter cube have 0.01625 moles of HCl. That is unreacted after the reaction with eggshell, and in 250 centimeter cube, these moles could be X. So if you find the value of X over here, so X would be equals to 250 into 0.061625 divided by 25. So here you would get 10, and it will be 0.1625. So 0.1625 are the moles of hydrochloric acid which are unreacted after the reaction with
यारी जी पाल है
after the reaction with unreacted
मैं
which
प्रेशर
are
कम कराएंगे टेंशन के लिए था
eggshell.
ये वीडियो कैसा पढ़ा रही है बता
Unreacted after reaction with eggshell. Is this understandable to everyone? If anyone have any question to ask. Yes. Is this clear?
Yes, sir.
Okay. Now, what they are saying, calculate the amount in moles of calcium carbonate that reacted with excess of acid. Okay. Use your answer to calculate the percentage by mass of calcium carbonate in eggshell. Show your working. Okay. So, if you see, initially the solution that we have used of hydrochloric acid, sorry, my bad. We have used this volume and this concentration. So from this volume and this concentration, what I can find the initial moles of hydrochloric acid before any reaction, right? So from here, I can find the initial moles of hydrochloric acid before any reaction. So it's 100 centimeter cube and 2 mole per dm cube concentration. So initial moles of hydrochloric acid is equals to its volume times its concentration divided by 1000 to convert the volume into decimeter cube. So what value you would get over here? 0.2 moles, right?
Yes, sir.
So these are the total moles of hydrochloric acid initially. Here we got the moles of hydrochloric acid that is left after the reaction with eggshell. So the moles of hydrochloric acid which are actually reacted with calcium carbonate in eggshell are actually equals to 0.2 minus 0.1625. Can anybody tell me the answer, please? 5, 9 minus 2, 7, and 9 minus 8.
0.0375.
Okay, thank you, Ahmed. 0.0375. So these are the moles of hydrochloric acid that actually reacted with calcium carbonate in the eggshell. Okay, so if you look at the reaction number 1, which is the reaction between calcium carbonate and HCl, the ratio is 2 moles of hydrochloric acid are reacting with 1 mole of calcium carbonate, right? So if I have to find the moles of calcium carbonate, so moles of calcium carbonate must be equal to the moles of hydrochloric acid divided by 2, because in the equation 1 mole of calcium carbonate is reacting with 2 moles of hydrochloric acid, so the ratio is 2:1. So I have to divide the moles of hydrochloric acid by 2, I would get the moles of calcium carbonate. Is this clear to everyone? So 0.0375 divided by 2 would get me, yes, please.
0.01875.
0.01875 are the moles of calcium carbonate. Now what they are saying, they further asking you to find the percentage by mass of calcium carbonate, the mass in the eggshell. So if you recall, the mass of eggshell that is used is 2.136 grams. See over here, right? So I have to find the mass of calcium carbonate. To find the mass of calcium carbonate, what I would do, I would multiply the number of moles of calcium carbonate with its MR, and the MR of calcium carbonate would be 100 or 100.1, I suppose. Yeah, 100.1, because calcium is 40.1, carbon is 12, and oxygen is 16. So it must be 16 times 3, 48, 48 plus 12, 60, 60 plus 40.1 is 100.1. Yes, answer please, the mass of calcium carbonate.
One 1.876.
1.876. Are you getting just this value, or you are getting the bigger value?
That's 76875.
6875. So these are the grams of calcium carbonate in the eggshell. I have to find the percentage mass. So percentage mass would be equal to 1.876875 divided by 2.136 times 100.
87.868. Actually 9.
87.869.
869.
So 87.9%. Yes, is this part is clear to everyone? If anyone have any doubt, please ask. Okay. Now, C part, name a suitable piece of apparatus which could be used to transfer 25 centimeter cube of a solution in step 8. So in step 8, if you see, we are transferring the 25 centimeter cube of a solution in the conical flask, and then few drops of indicator has been added. So it means we are going to perform the titration, and then due to titration, we use pipette to transfer 25 centimeter cube first in the conical flask, right? So I would write over here that it's pipette. Now part D, In step 4, a conical flask is weighed using a balance accurate to 3 decimal places and the mass recorded. Okay. The actual is placed in the conical flask and the mass increases by 2.136 grams. So see, we have took the two readings. First, we took the mass of conical flask. A conical flask is weighed, and then the eggshell is placed in the conical flask and the mass is increased by. So we are getting the two readings, right? Now calculate the percentage error in measuring the mass of this eggshell. So to measure the mass of eggshell, we took two readings, and if you see what they have told you that the least count is 3 decimal place, so it means its least count must be 0.001. So 0.0001 divided by 2 would give me the uncertainty that the any reading on the scale would be 0.005 uncertain, either positive or a negative. But here, as we have took the two values, so to find the percentage error, we do multiply this uncertainty by times 2, and the total mass that we have recorded is 2.136 times 100. So that would get me the percentage error. So can anybody calculate it and tell me the answer, please? Yes.
Zero point 0.0468.
0.0468. So this would be the percentage error. Okay. Now, next part is okay. Is this D part is clear to everyone? State the effect on the percentage by mass if eggshell is not completely dried in step 2. Explain your answer. So, yes, can anybody tell me the answer? What would happen if all the water is not completely dried? So, just think if, and what they are asking, what effect on percentage by mass, right? So, if the eggshell is not completely dried, then it means that instead of this value, there must be a greater value than this one, right? Is this understandable? Because this is the value that we have recorded from the balance. So if it's not completely dried, so we have a little greater value than this, but this value remains same because only the calcium carbonate is going to react with the acid, so it doesn't change, but the total mass would change. So this value remains same, and we are getting the higher value in the denominator. And if we do the calculation and find the percentage by mass, so this percentage mass would be lower than this one, right? Is this clear?
Yes, sir.
Okay. So for that, we would write that the percentage by mass of calcium carbonate would be less because the mass of eggshell recorded would be greater than the actual mass. Yes, if anyone have any confusion in this part, do ask. Is this clear to everyone? Okay. The student repeats the method using the same apparatus, but decides to use 0.1 mole per dm cube sodium hydroxide to reduce the risk of corrosion and damages to eye. Explain how this introduces a weakness to the experimental procedure. Yes. Okay. So how much sodium hydroxide we have used? We have used 1 mole per dm cube sodium hydroxide, right? And for that 1 mole per dm cube sodium hydroxide, the mean titer would be 16.25, right? So on using 1 mole per dm cube sodium hydroxide, volume of sodium hydroxide used is 16.25 centimeter cube, and we have used added it from the burette, right? So think 1 mole per dm cube solution then the volume used is 16.25 centimeter cube. Now think if instead 1 mole, as they have provided over here, that we would use 0.1 mole per dm cube concentrated sodium hydroxide, then what would be the volume of must be used over here? So if you will calculate 16.25 into 0.1 divided by 1. Yes, can anybody tell me the answer, please?
1.625.
1.625. No, 1 minute.
This calculation is wrong.
Yeah, this is wrong. 1 minute. The formula of the concentration is basically moles over volume, right? So we need the same number of moles. So if you see here, we have used the diluted solution. So the concentrated solution have a concentration of 1 mole per dm cube. Let me erase this. And the volume that is used is 16.25 centimeter cube. When we'll use the concentration 0.100 mole per dm cube instead of 1, then the volume that is used in the titration would be V, for example. So V would be equal to 1.00 times 16.25 over 0.1. Yes. So it's 0.1.
162.5.
162.5 centimeter cube. So it means we need this much volume of sodium hydroxide, and the capacity of the burette is just 50 centimeter cube. So it's a very large volume for the burette. So that's why we cannot perform the titration while using this concentration, that 0.100 moles per dm cube. Okay. So I can write over here, if 0.100 mole per dm cube sodium hydroxide is used, its volume would be 162.5 centimeter cube, which is very large volume for burette, as its capacity is 50 centimeter cube. Is this clear to everyone?
Yes, sir.
Okay. Now, let's move to question number 2. It is possible to measure the rate at which the potassium manganate, they have provided you the MR, diffuses through a permeable gel using the following method. Okay. Here there is a petri dish containing a permeable gel, a hole containing a sample of potassium manganate. Okay. The petri dish is prepared with a permeable gel, a hole of a diameter 0.5 centimeter. It's a diameter is kept in the center of the permeable gel. A sample of potassium manganate aqueous is placed into the hole, and at the same time a stopwatch is started. Okay. After 3 minutes, the diameter of the colored spot is measured and recorded. The diameter is measured every 3 minutes until there are 3 successive equal measurements. Okay. Student obtained the result shown in table 2.1. Okay, first tell me if everybody understood the method, that what is done over here. Yes.
This means the KMNO4 will grow, right?
Yeah, it would be spread on the gel. For example, if initially it is actually spreaded in this area, for example, after first 3 minutes, it would be spreaded to this area. And then after 3 minutes, it would be, for example, spreaded to this area. And then after next 3 minutes, it would be spreaded to this area. And they have took the 3 readings only. That's what they have told. Is this clear?
Yes, sir.
Okay. So here we got the results. Okay, they have taken there are 3 successive equal measurements. Okay, so these are the readings over here. Now, what they are asking you, plot a graph on the grid to show the relationship between the diameter increases of the colored spot and time used across to plot each data point. Draw a line of best fit. Okay. So at time 0, the diameter is 0.5. Here we have a diameter and here we have a time. So at 0, it's 0.5. So I would put a cross over here. Then at 3, it's 1.1. So 3 and 1.1. It would be over here. And then, no, it's not 3, sorry. Then at 6, 1.7. 6 and 1.7. 1.6, 1.7, and it's a 6. Yes. So at 6, it's 1.7. Then 9, 2.3.
Sir, it says diameter increase of this color spot. You're taking the wrong measurements.
Sorry, can you repeat again? Diameter increase of the color spot. Okay, diameter. Okay, thank you, Lisa. So this is our y-axis, and this is our x-axis. So 0 and 0 and 3 and 0.6. Okay, so we will start from here. At 3, it's 0.6. So it would be over here. And then at 6, it's 1.2. So 6 and 1.1, 1.2. Then at 9, 1.8. And 1.8. Okay, let me do this way. Afterwards, 12 and 2.2. So 12 is over here, and 2.2. This is 12, and 2.2 would be here. Then 15, 2.6, 15, 2.5, and 2.6. Then 18, 2.7. 18, it's 18, it's 2.7. Okay. So 18 and 2.7. Okay. It would be an MLS, I suppose. 21, 3.2. 21 is over here. And 3.2. Then 24, 3.4. So 24 and 3.4 would be this one. Then 27, 3.5. It's 25, 27. 3.5. And 33.6. Okay. At 33.6, and then we have a next three at 3.6, 33 and 36. So 33 and 36. Draw a line of best fit. Okay, so we have to draw a line of best fit. So here in this case, if first checking this one, after 25, it's 27 and 3.5. So it would be like this.
Sir, we can make the line of best fit curved like this.
Yeah, because if for example is another way of drawing a line of best fit would be like this and like this, but then examiner have mentioned that draw two lines of best fit.
So
In
we
this
match the
case,
two lines.
yeah. If the
Okay.
examiner have mentioned you that draw a line of two lines of best fit. Okay. And if
Right, sir.
this is showing like this, so you could draw a line of best fit is like a curve only. Okay. Now, what they are saying next, on the graph, circle the point which you believe to be the most anomalous. So, the most anomalous point, if you see, this one is the most anomalous, right? And as time is the independent variable and we are calculating the time, so it clearly means that on the graph, this point must be over here. So actually, this plot, this diameter is recorded at this time instead of 18. So it means that we have measured the time or we have recorded the time earlier than the time that we have mentioned over there in the table. Is this understandable?
So can you explain this point again?
Yeah. See, if you see the line, we can, with respect to time, we can conclude that this plot, this point that we have plotted over here would actually be over there on this point on the line, right? So if this point is over here, then it is indicating us that this point is at a time of around 16.5 minutes instead of 18 minutes, right?
Right, sir.
And we have mentioned the time that this time we have mentioned that this spot is at 18th minute, right?
Right.
But the graph is showing us that this point must not be at 18th minute, but instead it must be at 16th minute, right?
Right, sir. So the actual time is less than the one we recorded, right?
Ravi, can you repeat again?
The actual time is less than the one we recorded.
Yes. But there can be one aspect, another aspect would be there. Diameter increase, we are taking the change. Okay, yeah, we can write that. The actual time is lesser than the time recorded. Is this clear to everyone? Now, see over here, draw suitable tangent to the line at time t, at time is equal to 15 minutes. So this would actually also, telling you that you have to draw the graph over here, the curve over here, instead of a straight line. Calculate the gradient of your tangent. State both the sets of coordinates used in your calculation. The stated coordinates must be from your tangent. Give the gradient to three significant figures. Okay. If any one of you actually made the graph, if any one of you have a hard copy. Yes. Okay. So this can be a tangent over here. Okay, now let's take two coordinates. So let me take this one. It's at 2.1. And on y-axis it's 10 and 2.1, right? And let me take this one, 3 and 18.5. So 10 and 2.1, 18.5 and 3. This, can anybody calculate the gradient, please? Three minus 2.1 and 18.5.
0.10588.
0.
105 88.
double eight. Okay, so this is the gradient. Now, B part. Select the appropriate data from the table 2.1. Calculate the average rate of diffusion of KMnO4 in centimeter cube per minute. The average rate of diffusion of KMnO4 is equals to, okay, so the average rate, right? So if you see, the reaction would actually end it at 30 minutes, right? Here we are provided with the minutes, and the increase in diameter is from 0 to 3.6. So the average rate would be calculated by the change in the diameter divided by the time. So 3.6 over 30. Yes, can anyone tell me the answer, please?
0.12.
Okay. 0.12 centimeter per minute. Identify the independent variable in this experiment. So we have identified, and it's on x-axis, that's time. So time is the independent variable. F part suggests how the experiment could be made to more reliable. So if you see in this, we can't take the average, but what we can do, we can repeat the whole experiment and see the results are actually the same or not. If the results are same, then it means that it is reliable. Repeat the experiment again and see the results be same. Is this clear to everyone? Yes. Now, G part, another compound of a potassium which is colored is potassium dichromate 6 K2Cr2O7 Mr294. This compound is corrosive when aqueous. It is possible to use the method described earlier to determine the rate of diffusion of K2Cr2O7. Predict how the graph obtained for K2Cr2O7 would differ from that obtained from KMnO4. Explain your answer. So see, the MR would be given over here as well. So MR is the mass, and if there is a compound having a greater mass, its diffusion rate would be slower, right? And the one with a lighter mass would diffuse at, greater rate. So it means that K2Cr2O7 would be going to diffuse at a slower rate, and they are asking you to predict how the graph obtained. So we can say that it would be less steeper because the diffusion would be slow. So less steeper for K2Cr2O7. Because K2Cr2O7 diffuses slowly than KMnO4 as the MR of K2Cr2O7 is greater. Yes, is this point is clear to everyone?
Yes, sir.
Okay. Now, apart from temperature state, one variable which must be controlled when comparing the rate of diffusion of K2Cr2O7 and the KMnO4, as these two are aqueous, so their amount, and for the aqueous, the amount would be concentration. So concentration must be controlled. If we have to compare the result, then both the solutions having the same concentration must be used. Concentration of both K2Cr2O7 and KMnO4. Is this clear?
Yes.
Okay. Each part. Other than wearing eye protection, state one safety precaution students should take if they were to use potassium dichromate. So see here they have told us that it is corrosive, right? And instead of they are saying that try any other protection other than eye protection. So if it's corrosive, so it can cause harm to skin. So we can wear chemically resistant gloves. Okay. Now, each part 2. Another student suggests that to compare the rates of diffusion between K2Cr2O7 and KMnO4, it would be easier to place solid crystals of each of these compounds into the holes in two petri dishes of permeable gel. See, in the experiment over here, we have used their aqueous solutions, right? And the student is suggesting that instead of the aqueous solution, we would use a solid. So suggest two practical problems that this would cause. Okay. So there is a one problem can be as they are solids, so diffusion may not occur because solid doesn't diffuse, right? As solid do not diffuse, or might be they diffuse, so they diffuse very slowly. The other problem would be they are solid and we are using the aqueous solution into the gel, so there is a possibility that these crystals might not dissolve in the gel. The solid might not dissolve in the gel. Initially, we are using their solutions in water, so they are soluble in water. So, but we can't say that whether they are going to dissolve in gel or not. So, solids might not dissolve in gel. Is this understandable to everyone? If anyone have any doubt, any question, do ask.
Sir, can we write it won't diffuse too much? Like it will be less.
Yes, but this would be one point. For the other point, you have to write the solubility factor as well.
All right.
Okay. Okay, so see you everyone tomorrow, and tomorrow probably we are going to do February, March 2023. And I would further suggest do attempt the specimen paper, because specimen paper was published in 2022. So there might be a possibility that we can get a question from there as well.
All right,
Okay.
sir.
Okay, take care everyone. Allah Hafiz.
Allah Hafiz, sir.